Good afternoon, students. This is Arun, Assistant Professor, Department of EEE, DBS IT Company. So, in the previous class, basic variable impedance series compensator methods. There is a GCSC, TCSC, and TSSC. And now in this class, I'm going to discuss subsynchronous characteristics and basic operational schemes of those GCSC and TCSC and TSSC concepts. Okay. So firstly, I will start with the subsynchronous characteristics of those things. Okay. So actually, we discussed these subsynchronous resonance and subsynchronous oscillation damping in the previous sections. So in that one, the series capacitor line compensation can cause subsynchronous resonance. So series capacitor line compensation can cause subsynchronous resonance. So when the series capacitor resonates with the total circuit inductance of the transmission line at a subsynchronous frequency, that is FE. So that is equal to the frequency difference between the power frequency and one of the torsional resonant frequencies of the turbine generator set, that is FM. So that is when FE is equal to F minus FM, that is the difference between power frequency and torsional resonant frequencies of the turbine generator set. So here the variable impedance type series compensators do insert, that is either GCSC or TCSC or TSSC. So if you insert those a series capacitor in series with the line, do insert a series capacitor in series with the line. So therefore the behavior in the transmission network at subsynchronous frequencies is critical to their general applicability of unrestricted line compensation and power flow control. Okay, so here we are using a variable impedance type series compensators. So by using those, we have to insert a series capacitor in series with the transmission line. So after that, we will give the behavior in the transmission network at subsynchronous frequencies critical to the general capability for unrestricted line compensation and power flow control. So for that one, so as indicated earlier, the limitations imposed by the subsynchronous resonance, that is SSR, that is already discussed in the objectives of series compensation. So on the use of series capacitors prompted considerable development effort to find an effective method for the damping of subsynchronous oscillations. Okay, so in 1981, N.G. Ingorani proposed a thyristor controlled damping scheme for series capacitors, so which has been proven to provide effective SSR mitigation. Okay, they will that could be proven to provide the effective SSR mitigation. So although this scheme could be used to complement the series capacitor compensators discussed in this chapter. Okay, that is the subsequent research efforts found that the NGV damping, so the NGV damping principle can be extended to the basic TCSC circuit structure to make it substantially immune to subsynchronous resonance. Okay, so here I am introducing the NGV damping principle that will be extended to the basic TCSC circuit structure. Okay, why? Because to make it substantially immune to subsynchronous resonance. Okay, next, the basic principle of the NGH damper is to force the voltage of the series capacitor to zero at the end of each half period, and if it exceeds the value associated with the fundamental voltage component of the synchronous power frequency. So thus the NGH damper is basically a thyristor controlled discharge resistor. Okay, the NGH damper is basically a thyristor controlled discharge resistor. So in series with a di by dt labeling reactor, so operated synchronously with the power system frequency, that is F, in the region near to the end of the half cycle and the capacitor voltage. So this arrangement is shown in the diagram, that is this one. So this is the basic NGH SSR damper. So in this one I am taking a thyristor valve and inductor and a capacitor and a resistor to the transmission line. So by using this arrangement, we have to produce the waveforms for the line current I and voltage across the capacitor VC and current across the resistor. So in the first waveform, I am showing the current waveforms in a dotted line. So this waveform is in a sinusoidal manner, and after that we are taking the capacitor voltage across the capacitor voltage waveform. So this will looking like a sinusoidal waveform, but with the minor changes. And after that we have the resistor current across the resistor, that is showing like that it will some spikes in the waveform, that is IR. Okay, so the NGH damper clearly interferes with the process of subsynchronous oscillation build-up, since the capacitor voltage cannot respond naturally to a subsynchronous line current. Okay, so for that one, the actual effect of the NGH damper on capacitor voltage produced by a subsynchronous line current component is illustrated in this diagram, that is 6.24. So this gives the capacitor voltage and its fundamental component produced by a 24 Hz synchronous current under the constraints imposed by the NGH damper. So the waveform is looking like this. So in this one we have sinusoidal waveform. So it will give the IS and SC0 and VSC and GHF, that is the fundamental voltage, and next we have the normal voltage. Okay, so we have the waveforms like this. So for this illustration I am taking the frequency of the subsynchronous line current is chosen to be 24 Hz, and the NGH damper is operated at 120 Hz to discharge the capacitor at regular half cycle intervals corresponding to the 60 Hz power frequency. So in this one I already shown the diagram. So this diagram shows the 24 Hz sinusoidal line current, 24 Hz sinusoidal line current, that is IS. Okay, and next the corresponding sinusoidal capacitor voltage, that is VSC0. So sinusoidal capacitor voltage, that is VSC0, that is this one. Okay, VSC0, and that would develop without the NGH damper. The actual capacitor voltage, that is VSC NGH. So VSC NGH, and its fundamental component, that is VSC NGH F, obtained with the activated NGH damper. So that is this one. Next, so inspection of this diagram leads to an intersecting observation that the NGH damper shifts the capacitor voltage at the 24 Hz subsynchronous frequency so as to be in phase with the corresponding subsynchronous line current. Okay, after inspection we have this one, and in other words, the series capacitor with the NGH damper exhibits a resistive rather than a capacitive impedance characteristic at the 24 Hz subsynchronous frequency. So although this observation is made on a single illustrative example and not proven or generalized in a rigorous manner, so studies and field measurements indicate conclusively that the actual circuit behavior is in agreement with this resistive impedance characteristic is observed. Okay, so the reader may already see the striking similarity between the NGH damper and the TCSC circuit, the former being composed of a thyristor control resistor, that is R, and the latter of thyristor control reactor, that is TCS, both in parallel with the series compensating capacitor, that is in the previous circuit diagram. So although the TCSC circuit configuration was originally convenient for the realization of variable series capacitor, and the circuit similarity suggested that the possibility to use it also to implement the NGH principles of SSR mitigation. So it has been discussed that the PCR, that is thyristor control reactor, when operated within the TCSC to increase the effective capacitive impedance and reverses the capacitor voltage in region near to the end of each half cycle corresponding to the power frequency. So thus it can be expected that this synchronous charge reversal, just like synchronous discharge of the capacitor, synchronous discharge of the capacitor in the NGH scheme will interfere with the normal response of the capacitor to a subsynchronous current excitation so as to hinder or prevent the buildup of subsynchronous oscillation. So however, it is also obvious that the charge reversal in contrast to the subsynchronous discharge action of the NGH damper does not result in the dissipation of any energy. So that is ignoring circuit losses. Okay, and thus SSR mitigation by actual damping through the extraction and the dissipation of energy from the resonant LC circuit cannot take place. Okay, next. So in order to draw the parallel connection between the operation of TCSC and the NGH circuit, the voltage waveform obtained across the series capacitor is illustrated in this diagram. So this is a diagrammatic representation of the capacitor voltage and its fundamental component. Okay, the capacitor voltage, there is VSC0 and its fundamental component, that is VS TCSF, produced by a 24-Hz synchronous current under the constraints imposed by the TCR, executed capacitor voltage reversal. Okay. So here we have capacitor voltage, that is VCS TCSC, VS TCSC, and the fundamental component of that one, that is VS TCSCF, and we have the current value, that is IS. Okay, so for the previously considered 24 Hz subsynchronous current excitation with the regular half cycle 60 Hz capacitor voltage reversal characterizing the operation of the TCSC in the capacitor region. So the figure 6.25, that is this one, gives the similarity to the 6.24, that is this diagram. So there is some similarities for this one. So it shows the 24 Hz line current is IS, that is IS. The corresponding capacitor voltage, that is VSC0, that would develop without the TCR executed charge reversals. Okay, so the actual capacitor voltage, that is VS TCSC, and its fundamental component, that is VS TCSCF, obtained with periodically repeated charge reversal. Okay, so next, inspection of this figure reveals that the charge reversal shifts the fundamental 24 Hz voltage component so that it leads the corresponding 24 Hz line current by 90 degrees. So in other words, the TCSC circuit exhibits the impedance characteristic of an inductor at subsynchronous frequencies. So whereas the NGH damper with actual energy dissipation establishes charge reversal transforms for the series capacitor, and the TCR executed charge reversal transforms the impedance of the series capacitor into that of an inductor in the subsynchronous frequency band. So this observation is evidently important since it would indicate that the TCSC compensated line could not cause or participate in a subsynchronous resonance. And next, the general validity of the above observation is not proven rigorously to date, and applicable relationships for the impedance versus frequency characteristics of the TCSC. So in terms of the relevant circuit and control parameters, those are XL, that is the reactance across the inductor, and XC, that is the reactance across the capacitor, and alpha or sigma are not available in the form of mathematical expressions. So however, extensive studies, computer simulations, and the actual tests in prototype installations seem to indicate that the TCSC is substantially neutral to subsynchronous resonance and would not aggravate the subsynchronous oscillations. And the single condition for this important circuit property is that the charge reversal must take place. Okay, the charge reversal must take place at equal half period intervals corresponding to the fundamental system frequency. Okay, So with varying delay and conduction angle of the TCR, that is alpha and sigma, this condition actually stipulates that the center of different conduction angles remain fixed to the successive half period intervals, so independently from the freewheeling delay angle. So in other words, the conduction angle in the total operating range is to be symmetrically positioned around the zero crossing of the capacitor voltage. So evidently, it is increasingly difficult to satisfy this condition with decreasing delay angles, since with the correspondingly increasing TCR conduction, the locations of the capacitor voltage zero crossings are previously explained. That is for the TSSC and TCSC conditions increasingly influenced by the line current. Okay, and as shown above, the TCSC circuit arrangement with proper gating control can be made immune to subsynchronous resonance, that is SSR, and this mention can of course be extended to the TSSC. So in which case the TCR conduction would be kept at a minimum and used exclusively to achieve SSR neutrality, that is SSR means subsynchronous resonance. So actually in a large series capacitor compensator, probably several basic TCSC circuits would be connected in series and most of them would be operated with the TCR fully or fully off to minimize the harmonics and operating losses. So the behavior of NGHSP and TCSC under subsynchronous system conditions also make a convincing case for the subsynchronous neutrality of GTO thyristor controlled series capacitor, that is a GCSC, presented in the previous concept. And for this compensator case, the capacitor voltage is forcibly kept at zero and the zero crossings of the fundamental capacitor voltage by the normal GTO valve operation, except when the valve is fully off to provide the maximal capacitor compensation. So however, there would be no significant loss of compensating voltage. Okay, there is no significant loss of compensating voltage if a minimum turn of delay angle, that is gamma, so that is equal to gamma minimum, so would be maintained, which would allow the controlled synchronization of the capacitor voltage to the power system frequency and thereby ensure immunity to subsynchronous resonance. Okay, so up to now we discussed about the subsynchronous characteristics, and now we are moving to the next concept, that is basic operating control schemes for GCSC, TSSC and TCSC. So the function of the operating or internal control of the variable impedance of compensators, that is nothing but GCSC, TSSC and TCSC, is to provide appropriate gate drive. So it is to provide appropriate gate drive for the thyristor valve to produce the compensating voltage or impedance defined by a reference. So the internal control operates the power circuit of the series compensator, enabling it to function in a self-sufficient manner as a variable reactive impedance. So thus the power circuit of the series compensator together with the internal control can be viewed as black box impedance amplifier, and the output of which can be varied from the input with a low power reference signal. So the reference to the internal control is provided by the external or system control, so whose function is to operate the controllable reactive impedance so as to accomplish the specified compensation objectives of the transmission line. So thus the external control receives a line impedance, current, power or angle reference, and within measured system variables. These derives the operating reference for the internal control. So as seen, the power circuits of the series compensators operate by rigorously synchronized current conduction and blocking control, which not only define their effective impedance at the power frequency but could also determine their impedance characteristic in the critical subsynchronous frequency band. So the synchronization function is thus a cornerstone of a variable internal control of a viable internal control. So here we are using the additional functions. So these additional functions include the conversion of the input reference into the proper switching instance, which results in the desired valve conduction or blocking intervals. So here I will show the internal control schemes of these GCSC and TSSC and TCSC. So the internal control is also responsible for the production of the main power components, that is valve, capacitor, reactor, by executing current limitations or initiating bypass or other protective measures. So structurally, the internal control scheme for the three variable impedance type compensators, that is GCSC and TCSC and TSSC, could be similar. Okay, so subsequently, their function is simply to define the conduction or the blocking intervals of the valve in relation to the fundamental component of line current. So this requires the execution of three basic functions, that is synchronization to the line current, and another one is turn on and turn off delay angle computation, and another one is gate signal generation or gate firing signal generation. So these functions obviously can be implemented by different circuit approaches with different advantages and disadvantages. So in the following three possible internal control schemes are functionally discussed. Those are one for the GCSC, and the other two for the TCSC power circuit arrangement. So either of TCSC schemes could be adapted to the TSSC. Okay, so GCSC, TCSC and TSSC. So here we are showing three possible internal control schemes for the GCSC, TCSC. So the control scheme for the TCSC is applicable to the TSSC also. So TSSC is subsynchronous resonance would be an application concern. So I will show the first diagram. So an internal control scheme for the GTO, there is the GCSC, that is GTO control, series capacitor, that is GCSC. So this one, okay, so this one gives the functional internal control scheme for the GCSC. There is the first diagram, and coming to the B, these are the associated waveforms illustrating the basic operating principles. So in the first diagram, I am taking reference signal, that is DC reference, and we have synchronous timing circuit, that is PLL circuit, and we have voltage to turn off delay angle converter, that is VC of gamma is equal to K into F of gamma, and this is given to the current I, line current, and next we have the capacitor voltage, that is capacitor voltage sensing and processing circuit, and we have gate drive circuit, and we have one thyristor valve and one capacitor. Okay, by using this we produce these waveforms. Okay. So because of the duality between shunt connected GCSC and the series connected TCR arrangements, the control scheme is analogous to that shown in the TCR in the 5.19, that is in the previous concept, that is the shunt compensation. So this diagram takes the four basic functions. So this one counts of four functions. So the first function is synchronous timing. So that is provided by phase lock loop, that is PLL circuit. So that runs in synchronism with the line current. So that is the first one, that is the PLL circuit, phase lock loop. So synchronous timing circuit. That is the first function. The first function is synchronous timing that provided by phase lock loop circuit. So this will runs in synchronism with the line current IA. So the second function is the reactive voltage or impedance turn off delay angle conversion according to relationship given in the equation, that is 6.8 and 6.8b respectively. So that is the second one. So voltage to turn off delay angle control. And next, so the third function is the determination of the instant of valve turn on when the capacitor voltage becomes 0. So the third function is the determination of instant of valve turn on when the capacitor voltage becomes 0. That is this one. And next we have the fourth function. So the fourth function is the generation of suitable turn off and turn on pulse for the GTO valve. Okay. So the operation of the GCSC power circuit and internal control is illustrated by the waveforms that is in the diagram B. So inspection of those waveforms show that with a black box viewpoint, the basic GCSC can be considered as a controllable series capacitor, which in response to the transmission line current will reproduce the compensating impedance defined by the reference input. So here the dynamic performance of the GCSC is similar to that of the PCR. So both having a maximum transport like the TD of the 1/2 of a cycle, and the main consideration for the structure of the internal control operating the power circuit of TCSC is to ensure immunity to subsynchronous resonance. And so present approaches follow two basic control philosophies. One is operate the basic phase lock loop, that is PLL, from the fundamental component of the line current, and in order to achieve this, it is necessary to provide substantial filtering to remove the super and in particular the subsynchronous component from the line current, and at the same time maintain correct phase relationship for proper synchronization. So and a possible internal control scheme of this type is shown in the diagram, that is this one. So this is a functional internal control scheme for the TCSC based on the synchronization to the functional fundamental component of the line current. Okay. So in this arrangement, the conventional technique of converting the demand PCR current into corresponding delay angle, which is measured from the peak of the fundamental line current. Okay, that is this one, I. So here we are using error amplifier, that is PI controller, and here we have the IL current, that is it is given to the current to delay angle converter, and this will come from the synchronous timing circuit, that is PLL circuit, and we have filter and phase correction circuits and gate pulse generator, and these all are connected to the thyristor valve and reactor and capacitor, that is TCSC scheme, and we have one feedback, that is it consists of the reference signals VC reference and XC reference, and we have VC and XC. Okay, so the reference for the demand PCR current is as illustrated in the figure. It is usually provided by a regulation loop of the external control, so which compares the actual capacitor impedance or compensating voltage to the reference given for the desired system operation. So the second approach is also implies a PLL synchronized to the line current for the generation of the basic timing reference. And however, in this method, the actual zero crossing of the capacitor voltage is estimated from the freewheeling capacitor voltage and line current by an angle correction circuit. So the delay angle is then determined from the desired angle and the estimated correction angle, so as to make the PCR conduction symmetrical with respect to the expected zero crossing that is illustrated in this diagram. So this will give the same explanation for the previous diagram. So here a functional internal control scheme for the TCSC based on the prediction of the capacitor voltage zero crossing. So same arrangement we are taking. Okay. So but here we are using angle correction unit circuit we are using. That is the PCR gating control. That is the only difference between these two diagrams. Okay. So the desired delay angle in this scheme can be adjusted by a closed loop control phase shift of the basic time reference provided by the PLL circuit. Refer to the previous one. So the delay angle of the PCR and thus the compensating capacitor voltage, as in the previous case, is controlled overall by a regulation loop of the external control in order to meet the system operating requirements. Okay, so the regulation loop is relatively slow, so with a bandwidth just sufficient to meet compensation requirements. So thus, from the standpoint of the angle correction circuit, which by comparison is very fast, the output of the phase shifter is almost a steady state reference. So although control circuit performances are usually heavily dependent on the actual implementation, the second approach is theoretically more likely to provide faster response for those applications requiring such responses. So this is explanation for the basic operation schemes of GCSC, TSSC and TCSC. Okay, and in the next class I am going to discuss switching converter type large generators for the series compensators. Thank you for watching this video.